In lesson 16, we're going to look at another strategy to solve systems of equations. However, again, not elimination or substitution. One that's called Cramer's rule, in which we're going to use matrices and the determinants of matrices to help solve. But first, just to show the solution to the system in a way that hopefully you're comfortable with, we're going to solve this using elimination. Hopefully you recognize in the y column we already have opposites, so if we add vertically, x column should get 12x, constant column 24, divide both by 12, and our solution for x is 2. To find y, plug it back in. I'll use the top equation. You can plug it into either equation, but I'll use the top equation. 4 times 2 plus 2y equals 4. 4 times 2 is 8. Subtract 8 from both sides of the equation. 2y equals negative 4. 4 plus negative 8 is negative 4. Divide both sides by 2. And y is negative 2. So, we know our solution should be 2 and negative 2. Here's how we apply, again, what we call Cramer's rule, or how we can use matrices to hopefully make this process easier. So, what I'm going to do, I'm going to take, in order to solve for x, we'll solve for x first. I'm going to take the matrix and essentially replace the x column with the constant column, or answer column, or whatever you might want to call that column. So instead of 4 and 8, I'm going to write 4 and 20. Going to keep the y column as is, 2 and negative 2. And it will be a fraction here. So the bottom for both x and y, this won't change whether we're solving for x and y, will be 4, 8, 2, and negative 2. We keep the x column, we keep the y column. Okay, now to find the determinant. 4 times negative 2 is negative 8, minus 2 times 20 is 40. In the denominator, again, same process, find the determinant. 4 times negative 2 is negative 8. 8 times 2 is 16, so minus 16 should give us negative 48 over negative 24, which equals 2, which does in fact agree with our solution for x. Alright, very similar process with y. However, this time with our matrix, we're going to keep the x column and replace the y column with the constant column. So keep 4 and 8, replace 2 and negative 2 with 4 and 20. Same as with x. The denominator matrix is exactly the same. X column, y column. 4, 8, 2, negative 2. I already know, don't have to find it again. The denominator should equal negative 24. Obviously the determinant won't change. Numerator, 4 times 20 is 80. 8 times 4 is 32. We always subtract. Should give us 48, positive 48 over negative 24, which is negative 2. So, same as we had previously, using elimination. Same solution we found using elimination. X is 2, y is negative 2. So, Cramer's rule, it kind of honestly shortcuts the process for elimination, or makes a system out of elimination, if you will, by using matrices. So, again, quick run through the process here. To solve for x, replace the x column with the y column, keep the y column, find the determinant, over x column, y column. Solving for y, keep the x column, replace the y column with constant column, denominator, x column, y column. Alright, let's look at another example. Hopefully, after a few, you can easily internalize this process. Alright, so use, again, this is Cramer's rule. Use Cramer's rule to solve. So, in order to solve for x, going to replace the x column with, replace the x column with the constant column. Negative 1, 10, keep the y column. 2, negative 3. Denominator, 3, 4, 2, negative 3. Now find the determinant of both and simplify. Negative 1 times negative 3 is positive 3. 10 times 2 is 20. Subtract. 3 times negative 3 is negative 9. 4 times 2 is 8. Subtract. Negative 17 over negative 17 is 1 for x. For y, keep the x column, replace the y column with a constant column. On bottom, keep x and keep y. And again, this should be true always with Cramer's rule. Denominator shouldn't change regardless of which variable for which you are solving. So denominator should still be negative 17. For the numerator, 3 times 10 is 30, minus 4 times 1 is negative 4, minus a minus is a plus, so we should get 34 over negative 17, which is negative 2. So x is 1, y is negative 2. Okay, a couple quick examples here where there's no solution or infinitely many solutions, but where we either get a consistent and dependent or inconsistent system. Okay, so let's again solve this system using Cramer's rule. So to solve for x, I'm going to go a little more quickly this time so we can get to the heart of the matter. Solve for x, replace x column with constant column. Keep the y column. On bottom, x column, y column. 5 times 2 is 10, minus 8 times 2 is 16. 3 times 2 is 6, minus 3 times 2 is 6. Hopefully you recognize a problem right here. Didn't need to rewrite that. 10 minus 16 is negative 6. Over 6 minus 6 is 0. And hopefully you realize that we can't divide by 0. with y, keep the x column, replace the y column with constant column, bottom, x column, y column. We already know the denominator should again be 0. On top, 24 minus 15. 24, 15 is 9 over 0. And of course that is undefined. This is an example where the numerator is a constant that isn't 0 and the denominator is 0. That means it is inconsistent. This is the example where we have two parallel lines that never intersect. So that's when numerator is a constant that's not 0 and denominator is 0. Inconsistent, no solution. Next example. Again, using Cramer's rule to solve for x, replace 3 and 6 with 5 and 10. Keep the y column on bottom, x column, y column. 5 times 4 is 20, minus 10 times 2 is 20. 3 times 4 is 12, minus 6 times 2 is 12. And in this case, we get 0 over 0, which, like the previous example, is still undefined, but of course presents a problem. Solving for y. Keep the x column, replace the y column. Denominator, keep the x column, keep the y column. 3 times 10 is 30, minus 6 times 5 is 30. 3 times 4 is 12, minus 6 times 2 is 12, and again we get 0 over 0, which is undefined. So, in this case, when we get 0 over 0, not some constant over 0, but specifically 0 over 0, this is consistent and dependent. So this is the case, and you may have recognized, we should probably look at the previous example with that as well, but this is a case where the lines overlap. If you look at our system, the bottom equation is just the top equation multiplied by 2, so anytime you multiply everything in the equation by the same number, it doesn't change the value, so they're essentially the same equation. So this has a consistent dependent system, is where the lines are exactly the same, and it has infinitely many solutions. If you can see in the previous example, the inconsistent system, the constants for x and y are the same, the values are different here, so they're not the same line, but because the same coefficients for x and y, they have the same slope, so different lines but parallel lines that never overlap, therefore have no solution. So again, previous example, inconsistent, no solution. Constant over 0, constant over 0. Consistent, dependent, well, we get 0 over 0, infinitely many solutions.